Hello friends, in this video I'll be discussing critical connections in a network. So the problem statement is like there are n servers numbered from 0 to n minus 1 and those servers are connected by undirected server to server connections. So if we see the term connections, if we correspond this in terms of graph, we find that it is nothing but edges. Okay, and servers are nothing but vertices. Okay, so basically the problem statement is nothing but like there will be an undirected graph, and what we need to do is that we need to find the edge on removal of which it makes the graph disconnected. A critical connection is a connection that if removed will make some server unable to reach some other server. It means like we need to find the connections, the connections that is nothing but the critical connections on removal of which it makes the graph disconnected. So if we see this, that is the edge joining the server 1 and 3, we find that on removing of this edge we'll get two separated components of a graph. So 1 comma 3 is a critical connection. Okay, so like there can be more than one critical connections in this graph, so we need to return only one connection. So input will be number of vertices and connections, which is nothing but vector inside vector. So output will be the connection, the critical connection on removal of which it makes the graph disconnected. So basically this is nothing but bridge. Okay, so bridge means the edge that joins the vertex, and on removal of this edge it makes the graph disconnected. So the concept of bridge is same as that of articulation point. Okay, like we need to find the load time and discovery time. We need to use DFS algorithm to traverse the graph. Like we need to create a DFS tree for this graph. Then after creating DFS tree, we need to find the low and discovery time of each vertex, and we need to apply this formula. Like load time of vertex V must be greater than discovery time of vertex U. So we need to apply this formula. In articulation point, there are two rules which I've already discussed in my previous video. But in this video, like the concept is same as that of articulation point. So if your articulation point is clear, then you can easily understand the concept of this problem. We need to use this formula, that is low of the child vertex must be greater than the discovery of the current vertex. So if this is u, vertex u, and this is vertex v, okay, like there are two vertex u and v. So from u I went to v, discovery time of u is 1. The flow of DFS traversal with respect to each vertex, okay, the flow of DFS traversal, so it's 1. Discovery time of v is 2 because from u we traverse to 2, we find v unvisited, so we leave vertex u and start exploring vertex v. Now if the load time of vertex v, if the load time, so load time means from a vertex if we reach to another vertex having lowest discovery time, suppose from vertex v we went to the ancestor of vertex u. Okay, so definitely this vertex will have lowest discovery time because we have started our traversals, graph traversals from this vertex only. So from this vertex we went to this, from this we went to vertex v. From v there is a edge, and that edge is known as a back edge to the ancestor. So if there is a back edge, it means that from vertex v, the vertex having lowest discovery time reachable is nothing but the ancestor. Okay, so the load time of vertex v will be less than vertex u. It is sure because we are reaching the ancestor of vertex u from vertex v through back edge. So load time of vertex v will be less than vertex u. So if load time of the vertex v, that is a child vertex, is less than the discovery time of the current vertex, vertex u, it means that if the load time of the child vertex is less than the discovery time of the current vertex, vertex u, it means that there is a back edge. Like on removal of this edge, still this child vertex will be in connection with the main graph. Okay. But now if the load time of vertex v, suppose this vertex v has load time 4, okay, load time 2. So if the load time of vertex v is greater than discovery of the parent vertex, it means that vertex v has no connection to the ancestor of this vertex, and it indicates that on removal of this edge we'll get vertex v as a different component, as a separated component from the main graph. So this is the logic behind bridge of a graph. So the concept is same, only we need to use this single rule, that is load time of vertex v must be greater than the discovery time of vertex u for u comma v to be a bridge of a graph. So with the help of this concept we are going to solve this problem. If there will be a vertex u and from u there will be an edge which is reaching to vertex v, where u and v are the servers. So u will be an articulation point if on removing u we can have more than two components. Okay, more than two different graphs. So vertex 1 is u and vertex v is 3. So on removing vertex 1 we can have 2 comma 0 and 3 as different component. So we need to print output in the form of a vector inside vector having u comma v. Okay, u comma v. So output is like u is 1 and v is 3. So already I've explained the rules that we need to follow in articulation point. The, first of all, what we need to do is that we need to convert these connections in terms of adjacency list so that it can be represented in terms of graph. Okay, so input will be number of vertices and vector inside vector, that is the connections, which is nothing but the edges in a graph. So what I did was I have created adjacency vector which will create the graph in terms of adjacency list. I have applied for loop up to connections dot size, and with the help of this for loop I have created my graph. Okay, with the help of this for loop I have created this graph. Now next is I have created low and discovery arrays. So basically in order to find articulation point we need to use the concept of low time discovery time. Okay, and have created visited array and parent array. So we are going to perform DFS algorithm, like we are going to convert this input graph to a DFS tree. So in order to have this DFS tree we need to have DFS traversals, and with the help of this tree we can get our load time and discovery time of each vertex. So I have created load time, discovery time, visited and parent array. Next, in next step what I did was I have initialized my visited array and parent array. So visited array will be false. Okay, all the vertex is not visited currently. Next, I need to return vector inside vector. So I have created this answer vector which will be containing the articulation points. Okay, and with the help of this for loop, what I did was I have called DFS function. So basically I'll be applying DFS algorithm. So I've created separate DFS function which will be recursive in nature. Okay, and this DFS function will help me to have my critical points stored in this answer vector, and finally I'll be returning this answer vector. Okay, yeah. So we need to use discovery time and load time in order to check whether the child vertex is having some connection with the ancestors of parent vertex. Okay, so let's see the DFS function. So inside DFS function, I have passed graph, I have passed the current vertex. Like I'll be traversing this graph from vertex 0. Okay, from vertex 0, I'll be traversing the graph, visited array, low array, discovery array, parent array, and my answer vector. Okay, so initially the timer will be 0. Okay, and next for this vertex U, like in DFS, what we did was we selected the vertex and then called DFS for that vertex and mark that vertex true in visited array and start exploring the vertex. If there will be unvisited adjacent vertex, then leave the current vertex and start exploring the unvisited adjacent vertex. Basically, I want to create DFS tree. So I started traversing this graph from vertex 0. Okay, so from this, the next unvisited vertex is vertex 1. So visited of u is true, low of u will be what? It will be 1. Okay, so I'll be writing my discovery time and load time of each vertex on the top of this vertex in DFS tree. So my discovery time of vertex 0 will be 1 and load time of vertex 0 will also be 1. Okay. Next is I want to iterate the adjacent vertex of vertex 0. So if we see the graph, its adjacent vertex is 1 and 2. Suppose we got vertex 2 as its adjacent vertex. So I'm going to check. So vertex 2 is not visited. In parent array, what I will do is that I'll store the parent of each vertex. Okay. Next, what I will do, I will call DFS for the unvisited vertex. So right now, the unvisited vertex that we traverse from vertex 0 is vertex 2. So I'll call DFS function for vertex 2. Okay, for vertex 2. In visited array, I'll mark true for vertex 2. I'll increase the time of low and discovery inside the array. So for vertex 2, the low time and discovery time will be 2 by 2. So this is my discovery time and this is my load time. Okay. Discovery time means while traversing the graph using DFS, the time which is needed, like the time taken for visiting each vertex. Okay. Suppose initially vertex 0 is visited, so I'll mark it 1. Then vertex 2, I'll mark it 2, like this. And low time means lowest reachable vertex having low discovery time. Means vertex reachable having low discovery time from any vertex will be my load time. Okay, so I've already explained this in my previous video. So for vertex 2, I'll increase load time and discovery time. Then I'll start exploring vertex 2. So from vertex 2, I got vertex 1. So what I will do is that I'll call DFS function for vertex 1 because vertex 1 is my adjacent unvisited vertex. I will mark vertex 1 as true in visited array. Then I'll increase the load time and discovery time. So for vertex 1, load time and discovery time will be 3. Okay. Yeah. So from vertex 1, what I will do, I will start iterating the adjacent of vertex 1. So adjacent of vertex 1, unvisited adjacent is vertex 3. So what I will do, I will call DFS for vertex 3. So again, load time and discovery time for vertex 3 will be 4 by 4. Means it's the load time is 4 and discovery time is also 4. Okay. And I'll mark visited for vertex 3. So basically I've visited 0, 2, 1 and 3. Now from 3 there are no unvisited vertex, no adjacent vertex are there. So I'll return back to the caller. So the caller of vertex 3 is vertex 1. So from vertex 3 I'll be returning back to the caller that is vertex 1. It means that I'll be returning back to this statement. So from this line I'll start executing this. So what I will check is that I'll check for the low value whether it is changed or not. So so my u will be what? U is the current vertex. So from 3 I return back to vertex 1. Okay, so vertex 1 is what? Vertex 1 is u. Vertex 1 is u, and star it is 3. So what I will do is that I will check for low of vertex 1. So low of vertex 1 is what? Low of vertex 1 is 3. And low of star it is what? Low of star it is 4. It means that this vertex will have the low time 3. So this statement is used to check for a vertex u having child vertex v if there is a connection for this child vertex to u's ancestor. Okay, so if there exists a connection, then I need to change the low time of u. Okay, because u can reach to the vertex having lowest discovery time from this route. Okay, so I'm repeating again. Suppose u is the vertex and v is the child vertex. So this, with the help of this line, the role of this line is what? If the child vertex v has a connection to ancestor vertex of u, then we need to propagate the low value of the vertex u. Okay, because see, low time of vertex u was 3, and if suppose there exists a connection from for vertex v to its ancestor, so it will be automatically like less, it will be less than 3. So if it will be less than 3, then the low time of u will gets changed to the lowest time reachable vertex. Okay, so that's why we need to use this line to propagate the low time in the vertex. Okay, now next is what? The low time of this vertex is 3 because it remains same, because this vertex v has no connection to its ancestor. So if it has no connection to its ancestor, so if I'm going to remove this vertex u, it means that on removing we get two separate components of a graph. So this vertex u is what? It's a articulation point. So what I will do is that I will use the formula. The formula is what? If the low time of v, if the low time of v is greater than discovery time of u, discovery time of u. So our v is what? Our v is vertex 3. Low time of vertex 3 is 4. Discovery time of vertex u is 3. So 4 is greater than 3. It means that u is an articulation point. So if u is an articulation point, then store u comma v in an answer vector. So I'll be storing u comma v in answer vector and start iterating for another adjacent vertex corresponding to this vertex 1. So for from vertex 1, the other adjacent vertex is this vertex, vertex 0. But vertex 0 is already visited. So if it is already visited, I'll come to else if part. So inside else if part, we need to check whether the adjacent vertex 0 is parent of the current vertex or not. So u is basically the current vertex and star it is the adjacent vertex. So star it is 0 because 0 is the adjacent vertex of vertex 1. So I need to check whether this vertex 0 is parent of vertex 1 or not. So if it is not the parent, it means there is a back edge. So if we see the graph, we find that vertex 0 is not the parent of vertex 1, because parent of vertex 1 is vertex 2. Okay, it means that there is a back edge from vertex 1 to 0. So if there is a back edge, it means we need to change the low time of this vertex, because from this vertex we are reaching to the vertex having lowest discovery time. So the lowest discovery time is 1. So it means that we need to change the low time of the current vertex, that is vertex 1. So its low time gets changed from 3 to the discovery time of vertex 0. Okay, the discovery time of vertex 0 is what? 1. So its low time gets changed from 3 to 1. Okay. And therefore there are nothing to traverse, like no adjacent vertex is left. So again we'll be returning back to the caller of vertex 1, that is vertex 2. So we'll be returning back to this statement, to this line, and again start executing the instruction from this line. Okay. So again what we need to do is that the low value of this gets changed. It means that the low value of this vertex will also be changing. Okay, it will also be changing because it's like at a parent of this vertex, and using this path we are reaching to the vertex having low discovery time. So the the lowest low time of this vertex will be getting changed from 2 to 1. Okay, because using this path we are reaching to this vertex 0. So this line will help to propagate, will help to change the low time of the vertex. And now again we need to check the condition, that if the low time of the adjacent vertex, so adjacent vertex is vertex 1 with respect to vertex 2. So vertex 2 is my current vertex u, vertex 1 is the adjacent vertex v. So I need to check like star it. Okay, star it. So I need to check the low time. The low time of this is what? 1. And the discovery time of u is what? 2. It means that this will not execute. Okay, because low time is smaller than the discovery time. Okay, so next, there are no more adjacent vertex left. From vertex 2, control will come back to this part. Control will come back to the caller, that is vertex 0. So control will come back to this line. Again it will start executing the instruction below this, and its low time will be same because it's only the lowest what lowest discovery time reachable is same, that is 1. And we need to check this condition, that low time of the adjacent vertex, that is 2. If the low time of this vertex 2 is greater than the discovery time of the current vertex u, it means that u comma v is the bridge of a graph. Okay, so if we see the low time of vertex v, that is vertex 2, it's 1, and the discovery time of vertex u is also 1. It means that the discovery time of the child vertex is same as that of the parent vertex. So the statement will not execute inside if condition. Okay, so it will not execute. So the low time of child vertex, if it is greater than the discovery time of vertex u, then for u comma v will be the bridge. Okay, so the code is quite similar as that of articulation point. In articulation point we need to write two rules. Okay, like we need to check for the root, as well as in articulation point the rule was if low time of child vertex is greater than equals to the discovery time of parent vertex u. But in this case the rule is like the low time of the child vertex must be greater than the discovery time of the parent vertex. So this is the code for finding the bridge of a graph. So in case of bridge there is only one rule, that is the low time of the child vertex must be greater than the discovery time of the parent vertex. But in case of an articulation point there are two rules which I have already discussed in my previous video. So adding those two rules will convert this code into finding the articulation point of a graph. So code is somewhat similar. Okay.